Good morning, everyone. In this session, we are going to start the qualifying exam for the student Babak Rezaei. The title of his thesis is A New Metaheuristic Approach for Solving Vehicle Routing Problems. The committee members for this qualifying are me, Professor Frederico Guimarães from UFMG, as the advisor of the student. Professor Razul Enayatifar from Islamic Azad University. Professor Gilberto Reynoso Messa from PUC Paraná. And Professor Pukawashi Vaz Pena from the Department of Computer Science of UFOP. I would like first to thank all the members for accepting this invitation to join us. This qualifying is done in 3 parts. First, Babak will make his presentation in about 50 minutes, after which we start the questions from the committee members, and then we have a deliberation from the committee. As for those who are not familiar with the qualifying in FMG, the qualifying is done somewhere between the end of the 2nd year of the PhD and beginning of the 3rd year. And it's a moment where we can get feedback from external examiners about the research that's being developed. Babak, feel free to start whenever you're ready.
Okay. Okay. Can you hear me well, guys?
Yeah.
Officers?
Yeah.
Okay.
You?
Okay. So let's start. Let me first share my screen. Okay. Is it okay? The screen is visible for all?
Yeah.
Yes.
Yeah.
Yes. Okay.
Okay. So, okay, dear Federico, thank you for introducing the committee members and me. At first, I would like to say hello to everybody and welcome to my presentation. My name is Babak Rezaei. I'm a PhD candidate of Machine Intelligence and Data Science Laboratory from Electrical Engineering Department of Federal University of Minas Gerais. I'm going to present a new metaheuristic approach for solving vehicle routing problems as title of my qualification exam under supervision of Professor Frederico Guimarães. In this presentation, I'm going to talk about VRP, CVRP, and other variants, then a brief review of VRP solutions and methods. In section 3, we have a background about the imperialist competitive algorithm, or ICA. In section 4, we will talk about hybrid genetic search, or HGS CVRP. Then we have a very short description about the genetic algorithm and island GA. In sections 6 and 7, we have proposed algorithms, ICAGS and MPAGS. And finally, we have conclusion and future works. First, VRP, CVRP, and other variants. The VRP, which stands for Vehicle Routing Problems, first time introduced by Danzig and Ramsar in 1959. They proposed simple matching-based heuristics to route gasoline delivery trucks, and after that, the VRP has become one of the most interesting topics in operational research. The original form of VRP is a CVRP, or capacitated VRP. But what is the CVRP definition? In CVRP, we are going to find a set of routes to serve all customers while the overall route cost is minimal. But there are a few constraints here. First, all the vehicles are identical. It means all the vehicles have the same capacity and traveling distance. Second, all the customers should be served exactly once using only one route. Third, all the vehicles should start and finish at the same central depot. And fourth, splitting the delivery is not allowed. It means deliveries cannot be split between two or more vehicles. The VRP can be considered as a generalization form of the traveling salesman or TSP. TSP is one of the well-known classical problem in operational research, but what is the TSP definition? In the TSP, we are going to find the shortest possible route that visits all n given points once and return to the starting point. In this definition, we have three constraints as CVRP definition: finding the shortest route, visit all n given points once, and returns to the starting point. This is the reason that some VRP solvers first try to solve TSP and then convert the solutions to the VRP. In this slide, we can see one of the CVRP solutions. Here, we have the green dots as the clients, the red square at the central depot, and colored routes at the routes that each vehicle should travel to serve the assigned clients and return to the central depot. As it's clearly visible, each funded route can be considered as a TSP tour. VRP variants. For more adaptation with the real life, new constraints are added to the original VRP, and lots of the variants have derived, such as multi-depot VRP or MDVRP, VRP with time window or VRP-TW, a split delivery VRP or SDVRP, VRP with backhaul or VRP-B, and periodic VRP, PVRP, and many more. This graph shows a hierarchy of the VRP variants as a glance. VRP has a huge sort of practical applications that have made it more in focus, such as transportation, logistics, relief systems like disaster management, military purposes, communication, and many more. Okay, in this section, I'm going to provide a short presentation about the VRP solutions and methods. Okay, we know the VRP is an NP-hard problem, so it needs exponential time to be solved optimally. For solving the VRP, two approaches can be considered: exact methods and approximate methods. But what is the difference between these methods? Exact methods obtain optimal solutions and guarantee their optimality, but approximate methods generate high-quality solutions in a reasonable time. There is no guarantee of finding a global optimal solution. Exact methods here, because the VRP is NP-hard and its complexity, the exact methods only can be applied to the small instances. So if the number of the customers exceeds 200, exact methods cannot solve it consistently, and problem cannot be solved in reasonable time. The most successful exact methods in the literature are branch and bound and branch and cut. Approximate methods, we have two types of the approximate methods here: heuristics and meta-heuristics. Heuristics are designed to solve specific problems, but meta-heuristics are general-purpose algorithms to solve almost any optimization problem. And this slide shows a general view of the classification of VRP solution algorithms. Now we are going to talk a bit more about heuristic and meta-heuristic algorithms, but not in detail. Only few algorithms that are more important in the literature will be discussed. In class of constructive and two-phase heuristics, we can mention saving methods by Clark and Wright, insertion method by Moll and Jameson, sweep algorithm by Gillett and Miller, and root first, cluster second by Newton and Thomas. In class of classical improvement, K-opt by Lean is one of the most important algorithms in heuristics and will be most used in the VRP. In this algorithm, k edges are removed and replaced by k other edges. 2 opt and 3 opts are most common used forms of this algorithm. Or opt by or in 1976 is another classical improvement. It relocates a string of 1 to lambda consecutive customers. Lambda interchange by Osman in 1993 that exchanges 2 strings that have at most lambda customers each. Relocate, which is removing k consecutive customers from their current route and reinserting them elsewhere. Swap is swapping consecutive customers between different routes, and 2-opt star that exchanges tails of 2 routes. Meta-heuristic algorithms are designed to tackle large size problem instances by providing solutions in a reasonable time. In designing a meta-heuristic, 2 opposite criteria must be taken into account. First, diversification, which is exploration of non-explored regions of the search space. And second, intensification, which is exploring promising regions in the hope to find better solutions. Meta-heuristic algorithms are divided into 3 major categories. First, local search algorithms like tabu search, simulated annealing, variable neighborhood search, iterated local search, and GRASP or greedy adaptive search procedure. Local search methods explore the solution space by moving at each iteration from a solution to another solution in the neighborhood. Second, population-based algorithms like genetic algorithm, particle swarm, and colony optimization, evolutionary algorithms, scatter search, and memetic algorithms. Population-based heuristics evolve population solutions which may be combined together in the hope of generating better ones or better solutions. Third, hybrid algorithms. Hybrid algorithms are a combination of many successful strategies. From these categories, we can mention HGA or hybrid genetic algorithm, HGS or hybrid genetic search, KGLS or knowledge guided local search, and SISR or SISR or slack induction by string removals. In these 3 slides, I'm going to mention a few meta-heuristic algorithms that they are the most important algorithms in the VRP literature. The list is ordered by the year of publishing, and there is not another priority in the provided list. In 2001, unified tabu search is proposed by Cordio. In 2004, Prince proposed HGA, which was the first hybrid genetic algorithm for the CVRP. He also proposed the giant 2 representation and split procedure to cut giant 2 into CVRP roots. And adaptive large neighborhood search by Singer and Rock in 2007. Unified hybrid genetic search by Vidal in 2012. In this algorithm, giant 2 representation of Prince is utilized. In addition, they proposed population diversity using bias fitness, management of the penalized infeasible solutions, and an efficient local search. In 2013, a hybrid algorithm based on iterated local search, or ILS, is proposed by Subramanian. Arnold and Sorensen proposed knowledge-guided local search in 2019. Slack induction by string removals, or SISR, is proposed by Christian and Wendenberg in 2020. And finally, HGS CVRP is proposed by Vidal in 2020. The concept of the HGS CVRP is the same as the UHGS or HGS at short, but it includes swap star neighborhood, which is an additional neighborhood to exchange 2 customers from different routes without an insertion in place. Okay. A short review of available solution and methods in the VRP literature is finished, and now we are going to discuss the basic information that is required for this study. So let's start with ICA, or imperialist competitive algorithm. ICA was introduced by Atashbaz Gargari in 2007 as a new evolutionary algorithm. In contrast to other evolutionary algorithms, the ICA is based on socio-political process of imperialism. According to the original ICA, it includes following steps. First step is creating initial empires. In the ICA, the population is a collection of the countries. So, initial countries are generated, and based on the fitness value, n of them are selected as initial imperialists. Then, the rest of the countries will be divided among the empires based on their imperialist power or fitness. Using these formulas, the number of the colonies of each empire will be calculated. And this figure shows the initialized empires that you can see the imperialist one has better fitness value, so it has more colonies in its empire. Next step in the ICA is assimilation. Since the imperialists of each empire are acting as local optima, the other colonies in the same empire try to move toward their corresponding imperialists. This figure simulates the assimilation process. Revolution. To escape from local optima traps, a mutation in population is a need. In the ICA, this mutation is called revolution. Revolution rate is a parameter that determines the contribution percentage of the colonies in the revolution for each empire. Post-empires. Next step is post-empire. After revolution, colonies have new position. Their new cost will be calculated. If one of the colonies has better cost rather than its corresponding imperialists, their position will be exchanged, and the colony gets the power of the empire. This figure shows the process of the post-empires in one of the empires that we had. Then, total cost of each empire will be calculated by this formula, where TC of n is the total cost of the empire, and zeta in a parameter that defines the contribution factor of the colonies in the power of an empire. In real life, imperialists try to make their empires larger and larger, and this will happen by seizing countries from other empires. In the ICA, this event is simulated as a competition between the imperialists. In this competition, the weakest colony of the weakest empire will be taken by other empires by chance or by probability. An empire with more power has a higher chance to seize the colony. If an empire lost all the colonies, it will be removed from the empires, and its imperialists will be taken by the rest of the empires. And this figure shows a general view of the imperialist competition, where the weakest colony of the weakest empire, the blinking yellow one, will be taken by empires 1, 2, or 3 by the probability of P1, P2, and P3. All the mentioned steps, of course, except initialization steps, are repeated iteratively till only one empire remains in the search space. The weaker empire will collapse gradually by losing their colonies. At the end, only the most powerful empire will remain, and the algorithm will stop. In addition, the number of the iterations can be used as another option for stopping criteria. Now we have hybrid genetic search to talk about. In 2012, hybrid genetic search with advanced diversity control is proposed by Vidal, and in 2020, he proposed HGS CVRP, which is a specialized algorithm for CVRP with the same concept of the original HGS, but including a new swap star neighborhood search. This algorithm outperformed most of the recent proposed algorithms and is one of the state-of-the-art algorithms for solving CVRP. The HGS CVRP algorithm has following steps. Step 1, generating initial population that can be a combination of feasible and infeasible solutions. Step 2, generate new random solutions. Step 3, select 2 parents by performing a binary tournament selection and returning the individual with the best fitness. Step 4, recombine the parent to produce a new child or solution by applying an ordered crossover or OX. Step 5, insert trip delimiters in the crossover's output to produce a complete CVRP solution by the efficient linear time split, which is proposed by Vidal also. Step 6, improve the solution with a local search, which includes route improvement and pattern improvement. Step 7, insert the results in the population and apply population management for both feasible and infeasible solutions. And repeat steps 2 to 7 iteratively until a stopping criterion is met. And this figure presents the general structure of the HGS CVRP and the steps that we talked about. In the upcoming slides, genetic algorithm and island GA will be discussed briefly, very briefly. The genetic algorithm, or GA in short, belongs to the class of evolutionary optimization algorithms that is based on the fundamental Darwinian theory of evolution and biological reproduction. GA was developed by John Holland from MIT in 1960. GA has 3 important operators in the design of the algorithm: selection, crossover, and mutation. Selection. The selection operator is an operator for selecting members of the population for mating and recombination or reproduction. The selection process is randomly. There are 3 commonly used methods for the selection operator: roulette wheel selection, tournament selection, and elitism. Crossover operator is an operator that produces 2 offsprings from 2 parents selected for reproduction or recombination. Crossover may be 1-point, 2-point, or multi-point. In 1-point crossover, 1 bit of the 2 chromosomes is randomly selected and the 2 strings are interchanged at the point of the crossover, producing 2 offsprings. In 2-point crossover, 2 points are selected in the 2 chromosomes randomly, and 1 segment is interchanged between 2 parents, producing 2 new offspring. Mutation is the operator where 1 or more bits of the chromosome string are flipped with a fixed probability defined as mutation rate. This introduces diversity in the population and tends to extend the search space effectively. And this figure shows an example of the mutation in a binary encoded chromosome. See, we have a bit flipping here from 1 to 0. Island GA is a population distributed model of distributed evolutionary, or DEAs. The main difference between an island model and a single population model is the separation of individuals into islands. the islands interact by means of migration, and this is the only means of the communication between the islands. Migration has three parameters to define: migration size, migration interval, and migration policy. Migration size defines the total numbers of the individuals that will be sent by migration operator. Migration interval defines every certain number of the generations that migration operator will be run, and migration policy explains what is being sent. There is another structural definition in Island GA, migration topology, that describes which island sent individuals to which island. This is an example of a fully connected migration topology. In this topology, all islands can send and receive migrants from all other islands via migration path. Okay, in the previous slides, we discussed about what the others did, and from now we are going to talk about what we did in this study and what is our plan for the rest of the PhD period. First of all, let's start with the first proposed algorithm, or ICAGS. The ICAGS was the first idea of this study, which is a combination of the ICA and HGS CVRP to find more qualified solutions for CVRP. The ICAGS runs the ICA as the main algorithm and uses the power of the HGS in population diversity management to colonies of each empire. The motivation considers the exploration ability of ICA inside its empire and exploration capabilities of the HGS as a state-of-the-art in the CVRP solver. This figure shows a brief view of the ICAGS. In this view, the ICA has three empires. Each empire has its own imperialists and colonies. Managing the colonies is in the HGS tasks. As the general view of their algorithm, we have the ICA steps in our algorithm with some adaptation changes, except poses and empires that we will talk about in the steps. According to original ICA, the first step is creating empire. But here, there is a difference between the ICAGS and both originals of the ICA and AGS. We know that if we have higher quality initial population, it will lead the algorithm to find more qualified solutions. So, in the ICAGS, at the start, we generate feasible solutions randomly as the number of the initial empires, and all of the imperialists will be feasible solutions. The rest of this step is the same as the ICA. Next steps, according to original ICA, are assimilation colonies and revolve colonies. In ICAGS, we have some modification here. We have combined both steps in one step named assim revolve. Based on ICA, based on the original ICA, we have a parameter revolution rate, which is calculated by this formula. Actually, it is a percentage of the colonies that participate in the revolution. The assim revolve algorithm is presented here. There is a main loop to iterate in empires. The number of the revolved colonies will be calculated for each empire by its formula. In the nested loop, we do crossover and local search as the number of the revolved colonies. If assim type is a variable is false, then crossover will be done between two random selected colonies. But if assim type is true, then crossover will be done between best found solution overall and one random selected colony. The assim type is a variable which has defined in restart mechanism, and its initial value is false. Then local search and penalty management will be done by HGS. If there is no improvement for best solution overall, after NB iterations, restart mechanism will be run. This process repeats in each decade or iteration of the ICA. Okay. Another modification in the original HGS is adding a restart mechanism. In the original HGS, after a preset iterations, which is 20,000 iterations, the population will be regenerated totally if there was no improvement in the best found solutions. Or investigation in the results and required time to generate new best solution show that regenerating the whole of the population can make a big delay to reach to the new best solution. And in some cases, HGS cannot find better solution because the T of max is over. T of max is the limitation that's defined in the Widal paper. So we decided to modify this part of the HGS and define a new restart mechanism. But what is this mechanism? We have defined two restart types, totally and partially. Okay, in totally, the same as the HGS, 100% of the population will be regenerated. But in partially, 75% of the population will be regenerated and 25% of the population will be kept and moved to the new population. This slide shows partially restart in detail. If we suppose that this cycle is our current population, then by applying partially restart, we will have 75% of the regenerated population and 25% of the population from the current population. And we decided that this 25% be a mix of feasible and infeasible solutions. 25% from feasible solutions and 75% from infeasible solutions. Because the infeasible solutions have more potential to become feasible and make new bests, while the best solutions or feasible solutions have mostly the same fitness value after long iteration without improvement. And this is the algorithm for restart mechanism. Generally, if the number of the resets is equal to 1, the restart partially will be applied. Else, restart totally will be done. There is a variable asim type that will be set true if the imperialist cost is not equal to the best solution cost and the number of the resets is equal to 2. This variable is used in asim revolve to define the crossover inputs. Okay, because restart mechanism is one of the most important modification in the original HGS, and to make it more clear, I'm going to show you the restart procedure and its effects by examples. And as you can see, this is a screenshots of the algorithm output. We have several rounds of restart mechanism. I will show you how it works. For the first time, restart will be partially, as we described that the number of the resets is 1. In the next restart, imperialist cost is different from the last one. So again, we have restart partially. In the next restart, imperialist cost is equal to the last one. Okay, so we have restart totally. Okay, here, because the number of the reset is 2, we should compare the imperialist cost with the best found solution. Since they are equal, asim type will remain false. In the next restart, imperialist cost is different from the last one. So again, we will have the restart partially. In the next restart, again, we have restart partially because the values are not the same. In the next restart, imperialist cost is equal to the last one. So we have restart totally. Here again, number of the resets is 2, but in this case, the imperialist cost is not equal to the best found solution. So asim type, the variable that we described, will be set to true. In this slide, we can see how the restart mechanism can speed up finding the solutions. In the first screenshot, which is with restart mechanism, the BKS has found in 331 seconds, while in the second one, that is without restart mechanism, the BKS has found in 795 seconds. And in this slide, in the first screenshot, the best found solution is 88,992 in 749 seconds, while we do not have any improvements in the second screenshots, even by end of the algorithm. It shows that how the proposed restart mechanism can help algorithm to find best solutions more. Pulses and pairs is the next step of the original ICA algorithm. Since in original AGS, always the feasible solutions are sorted based on their cost, there is no need to perform this step in the proposed algorithm. And the final step, and the most important part of the ICA algorithm, is imperialistic competition. In this step, weaker empires are destroyed gradually by losing their colonies. For more diversification, we modified the original ICA in this step. According to the original ICA, the weakest colony from the weakest empire will be added to the empire which is selected by probability. But in the ICA AGS, one colony from the weakest empire will be selected randomly and will be added to a randomly selected empire. The underlines part of the slide show the differences between the original ICA and proposed algorithm. Now it's time to tune the ICA parameters and review experimental results. We need to tune 2 parameters for ICA, and the rest of the parameters are the same as the original algorithm. Initial imperialists and revolution rate should be tuned. For this purpose, 5 instances were selected randomly from different client ranges, and then we applied ICA on these 2 subsets of parameters. Subset 1 for initial imperialists and subset 2 for revolution rate. We do this perform for 10 independent runs with different seed numbers. This table presents the justification table to prove the ICA parameters. As we can see, most of the best averages are happened in row 5, which means 3 as initial imperialists and 0.5 as revolution rate. So the ICA parameters will be listed in this table. All the AGS parameters also will be remained unchanged. The experiments were conducted on 100 benchmark instances of Yuchua. Since these instances cover a wide range of the CBRP characteristics, they can be good enough challenges to verify the results of the proposed algorithm. As the original AGS, the code was developed in C++, and to analyze the results for recent algorithms from the Vidal paper are selected. Google OR tools, KGLS, or CSR, SISR, and HGS-CBRP. Since HGS-CBRP outperformed the other algorithms, and it is the base of our study, the proposed algorithm mainly will be compared by the HGS-CBRP. And as the provided results by the Vidal, the time limit T of max is calculated and considered for all instances. T of max for a smallest instance with 100 clients would be 320 seconds, and 3000 200 seconds for the longest distance with 1,000 clients. To measure the quality of the solutions, the gap of the algorithm will be calculated by this formula, where value is the solution value provided by the proposed algorithm, and BKS is the best known solution value for the instance. These three slides are experimental results and comparison tables. The bold items are the best found solutions. And this is the table 2. And this is table 3. And at the end of this table, summary of the results is provided. ICAGS has obtained better results in average gap, in maximum gap, and in the number of the found BKS. In this slide and the next one, we have analyzed the results in detail. In these tables, the term average means the average of the results from 10 independent runs with different seed numbers, and best means the best found solutions among the 10 independent runs. As we can see, ICAGS has found 51 BKS comparing with AGS with 44 BKS, almost 29% improvement in max gap for best found solutions. And in all the aspects of the calculated gap, ICAGS has performed much better than HGS. And in this table, the analysis is based on the number of the instances. First column, or better solutions, better results, indicates the number of the instances that ICAGS had have better performance in comparing with AGS. And the same concept for columns 2 and 3. Column 4 is the total number of the investigated instances, and column 5, improvement, indicates the percent of improvement rather than HGS. For instance, in case of the average solutions, ICAGS has provided better solutions for 66 instances, same solutions for 31 instances, and worse solutions for only 3 instances. So in this case, we have 63% improvement. If you need more detail, the Excel file, the Excel sheet is available, and I can show you the results. Okay, in this slide and next 3 slides, 4 random examples of the solutions are provided. Each slide contains convergence graph to compare both algorithms, ICAGS and HGS-CVRP. For instance, XN125, K30, both algorithms have found the BKS in the T of max, and their convergence curve are very similar. For this case, both algorithms found the BKS, but ICAGS provided the solution in almost half of the time consumed by HGS. In this case also, both found the BKS, and ICAGS has provided the solution in less than half of the time consumed by the HGS. And for this case, both algorithms could not find the BKS. HGS-CVRP has obtained the gap 0.06 after 1,484 seconds, and there is no other improvement, but ICAGS has reached to the gap 0.06 in 332 seconds and has continued improvement till gap 0.03 after 2,150 seconds, which is much lower than T of max. In comparison with the HGS-CVRP, ICAGS was more than 4 times faster. And in this section, I'm going to present the second proposed algorithm, MPHGS. MPHGS stands for Multi-Population Hybrid Genetic Search, which is a combination of ILAND-GAN and HGS-CVRP. What is done in the ICAGS is very similar to multi-population genetic algorithm, especially to ILAND-GA. The ILAND islands in the IGA or island GA simulate the empires in ICA, and the migration from the island evokes the imperialist competition in the ICA. The figures represents the general view of the algorithm. This example has 3 islands that HGS CVRP is managing the population of each island. There is a variable best solution overall that is accessible from all the islands, and they can write to and read from this variable. The process is very similar to ICHGS, but in MPHGS, the main algorithm is the island GA, and HGS CVRP is utilizing to manage population of each island. As the other evolutionary algorithm, the first step is creating initial population. Since the base of MPHGS is island GA, initializing the population of islands also will be done in this step. Like the ICIGS, we generate feasible solutions as the number of the islands. Then we generate the rest of the population. The number of the individuals for each island will be calculated by this formula, where N is the number of the initial population and M is the number of the initial islands. Okay, we have the same restart mechanism as ICHGS, where best island solutions is the best found solutions for each island, and best solution overall is the best error found solution among the islands. Here, the variable cross type, we change it to the cross type as acting the same as asymptotype in ICHGS and defines the type of the crossover inputs. The modification in GA process of the HGS is the same as what we did in the asym revolve in the ICHGS. In this step, the number of the mutated individuals will be calculated based on the mutation rate and HGS operators. I mean, crossover and local search will be applied to all of the selected individuals. As we mentioned previously, the only means of the communication between the islands is migration. So we need to define the migration policy and parameters. According to the proposed migration policy, the individuals migrates from the source island to the target island without any replacement. Source island is the island with higher or worse best island solution, and the target island is one of the islands that will be selected randomly. This policy helps the algorithm to maintain its diversification. By this policy, the islands with the worst fitness start losing their individuals and they drown gradually. And after migrating all individuals, the islands disappear from the map. Other migration parameters are migration topology, which is set to fully connected, so all the islands can communicate together and send and receive the migrants to or from all the other islands. Migration size, which is set on 1, it means in each migration interval, 1 migrants will transfer via migration path, and migration interval, which will be tuned during the experimental calculation. This algorithm presents the migration policy that is discussed before. And to stop the algorithm, we can consider one of the following conditions: when only one island remains on the map, or by considering the T of max, or by considering the number of the iterations without any improvements. And unfortunately, because the MPHGS algorithm is under design and evolution, the experimental results are not available for MPHGS yet. And the last section of this presentation is conclusion and future works. In this study, and till now, we proposed 2 hybrid meta-heuristic algorithms for solving CVRP. The first one was ICHGS, which was a combination of ICA and HGS CVRP. The ICA has a great ability to search the total solution space, and HGS CVRP is a state-of-the-art of algorithm for solving CVRP. and it has significant population management, diversity control, and improved local search. We performed the ICAGS on 100 benchmark instances of virtual, and experimental results show that ICAGS outperforms the HGS CVRP and provides solutions, provided solutions are superior. Second algorithm was MPHGS, which is a combination of Island GA and HGS CVRP. This algorithm is under design and coding, and experimental results are not provided yet. The future works and directions. Okay. The CVRP is the original and basic form of VRP, but the real-world problems are more challenging with several different constraints that can make the VRP problems more complex. The first planned work is extending the proposed algorithm to solve not only the CVRP, but also the other VRP variants like MDVRP, VRPTW, and PVRP. And next, one of the fast-growing technologies with tons of applications is drone technology. Drones can play significant roles in a variety of application areas like disaster management, like medicine scenes, transportation, last mile deliveries, and many more. The next step is trying to apply the proposed algorithms on vehicle routing problems with drones or VRPD. And the next slides are the time schedules. We are going to, for the rest of the 2021, we're going to review the qualification exam comments, finalizing the coding and designing of MPHGS and running the MPHGS on standard instances. For the first half of 2022, continue running MPHGS on standard instances, writing and submitting papers, modifying the code for different variants of VRP, and verifying the results on the standard instances. For the second half of 2022, continue verifying the results on the standard instances, writing and submitting paper, code modification to apply on VRPD, and apply the VRPD version on available instances. And for the year 2023, continue applying the VRPD version on available instances, writing and submitting paper, writing final thesis, and final PhD defense. Thank you all for your presence. I hope you enjoyed.
Thank you, Babak, for your very nice presentation.
You're welcome.
We now proceed to the second part of this qualification. And as a tradition in our program, we start the comments from the member that is the farthest from UFMG. In this case, I would call Razul. Razul, to start with your comments, okay?
Okay. Thank you. First of all, I want to thank you, UFMG, and especially Fred for having me here today. And I want to say hi to other two professors in the panel. So, Babak, about your presentation, that was good presentation. I got like answer for like 4 my questions. So I think that your presentation was good. But I want to start with some compliment. The organization of the thesis, I think, good. The obtained result was demonstrate your method quality. But there is a concern about your proposed method. Just so you know, I'm not very experienced and knowledgeable person about the VRP, as you might know. So I leave that part to the pros because I know some of the professors here are expert in that part. So I mainly focused on the meta-heuristic and bio-inspired algorithm part. Let me see my note. Okay, Babak, as I understand, the HGS is the source of your inspiration. Yes, am I right?
Yes, yeah.
Yeah,
HGS
yeah.
CVRP.
Babak, plenty of evolutionary algorithm out there in the literature. Did you come up with the idea of combining ICA with them, HGS? What did you see in the ICA?
Okay. Actually, I had a good experience with the ICA for my master thesis. It was a new approaches for for image encryption. I used the ICA and we got good results. Also, as I know, the ICA has great abilities in finding the solutions in the search space. It can deep in the solutions in the search space and find the best solutions in comparing with the other algorithms. Also, as I found that using the ICA is very easy, and converting the ICA from the digital and analog is too easy to to make it adaptation with the different types of the problems. I think it was my inspiration to use the ICA.
Okay, did you think the ICA by itself wasn't good enough for to be applied on the CVRP? You have to combine these two.
Yes, after I started working on the ICA, on this algorithm, ICHS, let me explain this before, because in the course that I had in the DCC, the heuristic and meta heuristic, I started developing a code based on the ICA for TSP, okay, and combining the ICA with the other local search algorithms to solve the TSP. So it inspired me to develop the code again for the VRP, okay, and especially for the CVRP. I try to use some using the local searches inside the ICA, but when I found that Vidal has a very good meta heuristic algorithm, which was HGS CVRP, and the code was based on the C++, was available on GitHub, and it will be available to use in this algorithm. I try to combine these algorithms, HGS with the ICA, and create the new, I think it was a new meta heuristic based on the something like multi-population. But Federico told me that there is a metaphor about using the ICA in the operation in the community of the operational research. So we decided to change the algorithm from the ICA to IGA or I-line GA, but we are trying to keep the features from the ICA and move them or copy them in the IGA or I-line GA. This is the reason that I'm trying to use the ICA or IGA as ICA in the second algorithm.
Okay, good. Babak, I have a question about SGS. You just use SGS. How much did you change the original SGS? You did say that you had some changes on the initial population, yes?
I try to keep the original ICA unchanged. Okay, the original parts.
No, I'm talking about SGS.
Yeah, I know about the
Okay.
HGS. I'm trying to keep the part that's related to the VRP. I'm trying to keep this unchanged. That it was from the local search, the penalized infeasible solutions, the population management. For these cases, I keep the structure of the HGS. Just I made some modification in the initial population and how to create the initial population. And the most important contribution is the restart mechanism.
Yeah.
That's I explained that this restart mechanism that I showed you the examples has a great effect on the finding new solutions and in decreasing the time that we need to find a new solution or the best solution.
Okay, you mean if you use just HGS, use your purpose HGS against the Vidal HGS, you have a better answer. Yeah.
Sure.
Okay. Okay. That's
with respect to Vidal, yes.
Yeah. No, I was convinced about with your experiment and result. So, Babak, this is my main question. In your thesis, you have two different methods. Am I right? First, you are trying to combine ICA with HGS as one method, and second one is your proposed
It's the
GA.
second, yes, the island GA.
Yes. Why there is two methods in one thesis? Did you think, for example, one of them isn't good enough to be presented for a PhD thesis? Because it seems each of them can be presented for each one thesis, so it makes me confused.
Okay, as I described at first, I started this process by creating this meta-heuristic or hybrid meta-heuristic for the TSP. Then I started working on the ICA. It was almost finished, and I asked Federico to check the results, to talk about the results, and the algorithms. And he told me that there, as I told you, that it's a metaphor about the ICA. Okay, so we decided to keep this algorithm as the first part of the thesis, the qualification, and move to a bio-inspired algorithm, like a genetic algorithm that there is no metaphor about it, and it's a widespread use algorithm in the operational research. So this is just like a strategy. Huh?
Yeah.
But we know that both algorithm, I have the results for the ICA-GS, and all the results as you saw in the text. It was great, but we know that if we apply the same operators in the ICA-GS that we have the experience about this, in the IGA, in the island GA, okay, we will have maybe the same results or even better results. Okay, we are working on the second algorithm to make it better than the ICA-GS. I hope so.
Okay, yes, I wrote down here in my note. You have plenty of results on ICA-GS, but there is no result. So at the end, which of these two you think has the better result?
I think the results.
The implementation of your proposed GA is not finalized yet.
No, it's not finalized. Okay. But I think the results will be the same. At least will be the same. But we are trying to make it better than the ICA-GS as an improvement to the first one, the first proposed algorithm.
So yeah, you answered all my question in your presentation. Just my last question about algorithm for 0.3. Yeah, when you decided to combine assimilation and the revolution, I didn't get the point. Why did you decide to combine these two parts in ICA?
Let me open my text.
Algorithm 4.3.
Algorithm 4.3. Okay. Let me share again. Oh, I can share this. Okay. You mean this algorithm?
Yeah. Why did you decide to? Because I had some experience on ICA. I didn't see the point. What you decided to combine assimilation and revolution.
Okay. In the ICA, in the original ICA, and in the assimilation phase, you have to do the assimilation for all the countries, all the colonies of each empire. Okay, but by this combination, that assimilation and revolution are combined together, we need just only the number of the revolt colonies participate in this case, and we do the assimilation only for the number of the revolt colonies.
Yeah.
And this can make the algorithm faster. Okay. You know,
Are you sure?
Yes, I did it. I tried. I tried before the combination. I tried the assimilation for whole of the empire, but the time that's consumes for assimilation was too big.
Okay. So you have the experiment about that, yeah?
Yes.
Okay. So you answered my rest of question. Okay, Fred, I'm done by now. Maybe in the I'll get back to him later. Now I'm done.
Okay, and let me, Federico. Professor Rasul told that he's not experienced about the VRP, and here I think it will be better to say that this study is not exactly the VRP, because I'm not working on the VRP phase of the solution. I was trying to make an improvement on the algorithm and make a meta heuristic, and using the VRP as an application. This is an application, and using the HGS from the VDAL, just to have better solutions, higher quality solutions in this hybridization. Okay. It was in parentheses.
Okay, Razul, thank you very much for your questions, your participation. So now we proceed to the second member. I would like to ask Gilberto Mesa. You can begin your comments and feedback.
Okay, thank you very much. Testing, 1, 2, 3, 1, 2, 3. Can you hear me?
Yes.
Perfect. Okay. Okay, first of all, thank you very much, Federico, Babak, for this invitation to be here, to have the opportunity to read your work, your proposal, in order to bring some comments, some discussion that perhaps is going to be useful for you, for your advisor, in order to continue with your work.
Okay.
The work is very, very interesting. The problem is very, very relevant, the way it is. Okay. New meta heuristics are always useful in order to solve different kind of problems. The VRP family of problems, to say it in a more broad sense, it's a very, very interesting concern. Now, at the end of your presentation, talking about this idea about working with drones and so on, I think it's a wonderful idea, because that's going to happen now. Okay, because that's a very, very actual problem. So is to congratulate you for the approach, for the ideas, also the structure of the work. I think is being well directed for your major aim, in this case on your work. So congratulations, okay, for you,
Thank you.
your advisor. And I have some comments on the PDF. I will send you the PDF. You know, always you will find some things, some points, some stuff over there. It's nothing to be worried about. And I have some questions, some suggestions for you, for your work. Okay. The first thing is just help me with this, because also I am more familiar with in an overall sense, with the meta-heuristic optimization, more multi-object optimization, and so on. So these kind of problems, I'm familiar with these kind of problems, with the VRP family problems. Okay. Help me with this. In this case, you are comparing with the work of Vidal. Okay, Vidal. Yeah. And then you are using this. You are using this scaling factor, okay, for the CPU time in order to have this fair comparison, okay?
Yes, sure.
Why that? I mean, what's the rationale behind that? Because I'm more used to think about function evaluations. I think I know the answer. I would like to hear from you that. Okay.
Okay. Yes, okay. For as a stopping condition, we can consider, I think, two approaches. Okay. Then the first one is reaching to the best known solutions that we know that they are in the literature, and the second one is the time. Okay, we can limit the time. Okay, and perform the algorithms to see how the performance of the algorithms is qualified in this in time limit that we have. I did this because in the Vidal paper, I don't know if you read the paper, he started the algorithms and running the algorithms in a certain time. We need this reasonable time to solve the problem, to solve the meta-heuristic problem. And this is what the meta-heuristic are going to do. They have to solve the problems in a reasonable time. If this time limit exceeds, I don't know how much it can be, you know, these solutions will not be applicable for the some, you know, useful applications, for the applications that may are going to use the meta-heuristic approaches. We can do we can perform the algorithm for a long period of time to solve the problems and reaching the BKS, or best known solution. But if we limit the time, that it was a T of max that was defined by the CPU time, it will be more, you know, reasonable, more sensible, that how this algorithm can provide the higher quality solutions.
Okay. In that, with that idea, because you say, okay, stopping condition could be, okay, reaching the best solution so far, okay, time, CPU.
Yes, yeah.
And then I will put a third one, which is this one about function evaluations. Perhaps it's because that's my area, working with complex simulations. Most of the time we say, okay, the budget, you have a budget of 100 simulations in order to do your best in order to find the optimal solution, or a reasonable optimal solution over there. Okay, so that is just because it was different, a little bit different for me. I like this idea about, okay, I will scale this in order to have a fair comparison. I like it, that idea. I don't know if right now that's the standard in this area. I don't know. But then, yes.
Sorry, if you allow me to make some comments.
Yes, please.
Actually, some complex, like the ones you probably more familiar with, the evaluation of the problem is the hardest, the hardest part of the optimization. It's the one that's more time consuming. Yeah. So in these situations, we consider the number of evaluations as the stop criterion. It's much more, it makes much more sense. But in logistic problems like this one, VRP, the evaluation is fast, so it's not an issue. So the problem is, so it makes more sense to use the time to evaluate the heuristics. So faster algorithms that reach the best solutions in less time are better. So this is the difference that I would like to remark.
Okay. No, thank you very much, Frederico. Also, in order to make my mind with the following comments that I have here. Okay, because that's nice. Okay, that's the idea is, okay, let's try to do this faster, the faster possible. Then I will enter with this idea about the database or how the scientific product is being presented. Because, for example, if time is important, it doesn't make sense, for example, for you, I will use a random graph. One of those convergence graphs that you have over there. It doesn't make sense to have then also some kind of distribution probabilities around this convergence path in order to evaluate, okay, at the beginning, for example, the HGS, for example, is quite better in the, for example, in the first 15 seconds or something like that. But then if you allow your algorithm, your proposal to go to 100 seconds, for example, then you will reach a better solution. So I don't know if that makes sense for you then in order to present those results, because right now it's the best solution. Okay, that's okay. It's the best solution or the best convergence path, perhaps, that is possible to find out here. But from the practical point of view, it's quite more interesting to have this, to see the most possible, the most probable result around, for example, 15 seconds, 100 seconds, 150 seconds, and so on. That makes sense for you or no?
Yeah, you're right. Yeah, it can be.
Okay. Also, I know that as you are taking those results from Vidal, perhaps Vidal is not reporting all that convergence path and so on. So that could be an issue or a problem, because those algorithms from Vidal, you are not implementing those algorithms, isn't it?
No, I'm not implemented those, but as I told you in the comments from the Professor Rasul, this algorithm, the code is available on the GitHub. Okay, and I got the code from the GitHub and run the code for these cases also. For the cases that I have brought the convergence curve, I run the Vidal code for these cases, and just for comparison between the results from the ICAGS and the HGS, I use both codes from the Vidal and my code also, but on the same machine, machine that we can compare the results together with the same CPU clock.
Okay, then you have full control in order to define a different way for the experiments and comparison. Okay.
Yes.
So perhaps if that makes sense for you, perhaps it's going to be useful to have this convergence path of all the runs that you are using in order to present the results, and also that brings very, very nice plots also over there. Okay. So perhaps that's interesting. Also, I would like to suggest, okay, for the tables that you have in order to present the results when possible for the algorithms, if you have full control to do that, they are nice graphs as the basic one are box plots, but also you have box plots with violin plots, and also you have critical differences plots. Those are very, very nice and very, very compact in order to depict a lot of information. So perhaps one of those solutions could be fit with your idea, with your work, okay, in order to present the results. Because it's a little bit overwhelming to see those tables, and we are expecting more tables at the end of this process.
Okay,
so
sure.
Perhaps you will like to think about that. Okay, that. I think I'm not quite sure. Perhaps Federico is going to be more informed than me. There are some competitions on those kind of instances, isn't it? Competitions in some conference about the problems related with the DRP family over there. Are you thinking about participating or something like that, or is not on the table that?
I didn't know about these competitions, but I don't know. We can discuss with Federico if we receive or find the results from the MPAGS, the second algorithm, and if we got better results in comparing with the first one, maybe we participate in the competition if Federico allow me.
No, I will try to remember about that, because it's not on my first level radar, but regarding all the information that is passing here every day, I remember about some competitions, perhaps in the GECO conference, perhaps, or perhaps in the IJN competition. One of those conferences, I remember something about VRP-like problems in that competition. So it is very nice, because you will do your best in order to find the best results, and let's see what happens. And for you, it's quite nice to report that on your work. If I can remember or find that information, I will also give you a hint about that.
Okay,
perhaps that's interesting.
Thank you. Yeah, it's interesting competition with the VRP. I don't know.
Yeah. Also about the hyperparameters, I don't know the experience when reviewing, for example, papers with new algorithms or something like that. Some of the times right now, people is asking a lot of questions, a lot of inquiries about the hyperparameters of the algorithm. So I don't know if you know the best your algorithm. I don't know if with that table is quite enough, but I'm trying to remember similar papers, and the study about the hyperparameter selection and so on is a little bit more expressive, more extensive. So perhaps you would like to take a look on that. Right now we were having some nice experiences using some meta-heuristics for meta-heuristics hyperparameter tuning. Okay? As Babak and Rezaei. I will put those comments also here in your work, Babak and Rezaei, which are techniques, methods in order to find the most suitable combination of hyperparameters, and you will find also some kind of nice information about the robustness of that set of parameters also. So perhaps that could be useful for you.
Okay, sure.
That one, figures, metrics. Okay. Okay, and about the layers on your algorithm, you say that this restarting mechanism is perhaps the most important stuff over here. Okay?
Yes, yeah.
So, and you told also that, okay, I have some experiments about that also over there. Perhaps it's going to be quite useful to bring those experiments also in your work in order to show, okay, it makes a difference. Okay? It makes a difference to have this restarting mechanism, and also because
I brought in the I didn't have in the text, but I brought some examples in the presentation to make it more clear.
Yeah, those examples, for example, I think that's going to be useful to put there with a different visual, because also that screen with all the lines is a little bit overwhelming. Okay, if that is objective to overwhelm the professor participating here in the defense, that's okay. But perhaps a different way to present that it makes a difference. And also, if I understand, for example, this algorithm from Vidal is not using a restarting mechanism, isn't it?
No, as I described in the presentation, when the iterations or generations reaches to a predefined iterations, which the name is NB iter, and the default value is 20,000. After receiving to this iteration, all of the population will be regenerated. Okay, this is only the restart that's in Vidal algorithm we have, but we change it in for different steps. In different steps, we restart or regenerate the population.
Because perhaps it's going to depend which one are your plans in order to write the paper, no? The journal papers that you are going to prepare to send and so on. Because one of the questions will be, okay, it's not the case that, okay, the algorithm beats, this case is better than that from Vidal. That's because of the restarting the restarting mechanism. It's not because of the imperialist part of the algorithm. So perhaps you are going to need some intermediary experiment, perhaps, I don't know, in order to show, no, it makes a difference, but also my approach in this case with the imperialist algorithm or with the MP approach is going to add a valuable improvement in this work. So depending on that, perhaps you will receive that question, perhaps.
Okay.
And I think that for me is just that. Which one are your plans for papers? Is just one or two papers, or the program? How many papers requires your program?
No. For paper, we are working on a paper based on ICAGS, and is almost finished, and we need to do some adjustment and to do some minor modifications, and we submit this paper. Then we will have another paper for the multi-population AGS, MPAGS, of course. Again, after the making modification on the MPAGS to be available for the other variants of the VRP. We will try to submit another paper, and also again after applying for the VRPD. I think maybe at least four papers we can submit by this thesis.
Okay, something among 3 and 4. And the programs, Federico, what are the requirements in your program for papers?
Here in our program, we require at least one journal paper.
At least one.
Above some limit. So that's the minimum requirement for the PhD. But
okay. No, so no props. No, here I'm pretty sure that here, you will find here at least 2 papers. Okay. So no worries. Yeah, at least. No, obviously, if you can bring 10 papers from here, it's nice. Obviously, as always. Okay, perfect. Okay, I think that from my point of view, I think is that, as I told you, some small comments around here in the PDF. I will send you the PDF, our small stuff. Also, please, those comments are because I am not familiar with the template that in the university. So if, okay, that comment doesn't make sense because the template is the way it is, okay, then omit that comment and just go on. Okay.
Okay. Okay. Thank you.
Okay. Okay. So one more time, thank you very much for this invitation to participate in this process, and that's all. Thank you very much.
Okay.
Thank you, Gilberto. Thank you very much for accepting the invitation, for joining us, and for all the comments and feedback about Babak's work. Thank you very much. Okay, we appreciate it. Next, please, Professor Pukawashi. You have the stand.
Okay, thank you. Can you hear me? Is that okay?
Yes.
Yes. Yeah.
First of all, thank you, Frederico and Babak, for this invitation. It's very nice. It's a pleasure for me to participate on this thesis. When Federico sent me an invitation, okay, I had a guy working on weak routing problem. Can you participate? Of course, yes. But when I saw the title, capacitated weak routing problem, I imagine Frederico is a crazy supervisor. It allowed a student to work on this classical version of VRP. For me, I never allowed a student of mine work on this classical version. Perhaps it's very difficult to improve some result on this version of VRP. I prefer to work on some other variants, but you did a good job, a very nice job. And when I start reading, I understand, because you decided to use state-of-the-art algorithm as a black box and increase and put something else. So it's a very nice way to work on CVRP, okay? And you did a very nice presentation. Congratulations. But regarding the text, you need to review in detail, because I can understand, I can read, of course, but sometimes you have some punctuation problems, missing a lot of commas, and some pronouns like which and that. It's a bit confusing, but for me, I can read, no problem. But for a native English, maybe the text didn't sound well. But okay. You have time for that, okay?
Yeah, okay, sure.
Well, I'm familiar with vehicle routing problem because my thesis I work on heterogeneous vehicle routing problem. I also worked with Thibaut Vidal in some this related problem, and Subramanian also.
Yeah, we know that.
I usually use local search meta risk, not populational meta risk. I know them, work with Thibaut Vidal, but in my papers, I also used local search algorithm. And when you use the Vidal algorithm, it was very nice idea to use them, as I also said. And let me see my notations. When I understand during your presentation all the mechanism that you modified. It's not clear during the test, but during the presentation was very, very nice to saw that modifications. And I believe that during the text, I will speak a little. I will do some comments about the test, and after I comment the algorithm. During the background and the review, you can use some, how can I say? For example, the heterogeneous fleet was the problem that I worked. The literature review, you put, for example, heterogeneous fleet with load constraint, two-dimension load constraint. This is not the classical heterogeneous fleet, so it's heterogeneous fleet plus something. And you did this during the literature review with some references. So I suggest you to put the reference of that problem, not the problem with something else. I don't know if it's clear, but in that case, in some other case, you do that. It's not the reference of the classical version, but the classical version plus something.
Yes,
okay?
You're right.
I think it's better to put some reference of the classical version of that variant.
Okay.
And about the figure 2.1 that you did on hierarchical VRP variants, it's not clear for me why you separate
About which one? I couldn't hear you well.
Figure 2.1.
Figure 2.1. Okay.
Yes, the hierarchy of the VRP variants.
Okay.
It's not clear for me to separate VRP and CVRP in two variants. And for example, why VRP with backhouse is a CVRP variant and not a VRP variant?
Of course, it's a VRP variant also. CVRP is a sub-variant from the VRP, from the original VRP, and the CVRP is the capacitated or the classical one. This hierarchy, I don't remember the reference that I found it here in. I found this hierarchy in the literature, and I add some other variants to the VRP version. But
yes,
I can find this reference and send you if you like to see.
Oh no, backhouse is just an example, but in my opinion, all of these variants, the open VRP, periodic VRP, they are also capacitated.
Okay. I got your point.
So it's in this direction. All that variants are capacitated. So it's a little bit confusing because someone can, multi-depot is not capacitated. No, it is capacitated. Okay. So it's not clear if it is a good hierarchy.
Okay.
If you allow me to interrupt, Puka.
Of course.
Maybe this figure, Babak, you can fix it by just merging the VRP box with CVRP.
Yes. Yeah, I got his point.
Because it's basically all these versions can refer to one on another. So it's but Puka is right.
Yes, sure.
And yes, this is the main comments about that figure, and the rest of the test, just some small comments, like I said, some small punctuation, verbs and pronouns. And you also asked why to implement two meta risk. Okay, that's nice for me. And I would like to also comment about the parameters. I believe it's important to use an automated program to do that, like arrays, as Professor Gilbert also said. It's important. Nowadays, it's very difficult to publish something just putting, my parameters are that. How you obtain that? Okay. So try to use arrays. Is a very nice package and not difficult to use.
Okay.
And about the implementation, I believe it's okay as you improved some solutions. Very nice to see that. And the feature works. You mentioned that you'd like to apply your method to some variants. Okay, it's a very good idea. As you obtain good results for CVRP, I believe that you also can obtain good results for other variants. And some of them, it's very easy to adapt, like multi-depot or something like that. But you also mentioned to work on VRP with drones.
Yes, yes.
There are some new variants on this problem. I have a student of my work in one of them. It's the Flying Side Quick VRP.
Yes, yeah, I read this paper.
Flying Side Quick TSP. And I'm afraid if you work on such kind of variant with vehicle and drones, to adapt the algorithm is not so easy because you have a vehicle, okay, normal vehicle serving the clients, the customers, but you also have several trips of the drone, and manage this trip is different to manage the route, the vehicle route. So I'm afraid of that. Which kind of variant are you have intention to work? Only drones or vehicle and drones?
No, this is the vehicle and drones in together. You know, I read some papers. It's not started completely, but I started reading the papers. I found that in some cases we can solve the problem using the VRP, the same as what we did, and then insert the drones inside the routes by considering some constraints that I think it was by Schimmer, something like this. The guy that has a paper, it was Schimmer in 2019. They have this paper from the German. They propose a method that first solve the problem using the VRP. Okay, then in the routes they start inserting the drones. Now it has a method that we need to inserting drones by considering the costs and the flight duration and the distance from the vehicle, and then the drone will back to the next client. That's the vehicle will be waiting for the drone.
Yes, you are right. But you have some extra constraint that's very difficult to deal. For example, the drone duration, and also the vehicle and the drone synchronization, because they need to arrive at the destination point together. Okay, so I'm not sure that adapting the algorithm for drone vehicle routing with drone is a good idea. Okay, because this extra constraint is very hard. But if you can adapt with solving the vehicle routing problem and add this extra procedure, for example, to deal with the drones, I believe you have a very nice job, because it's not easy to find. In fact, I never found in the literature, as I'm not wrong, the same algorithm to deal with vehicle routing and vehicle routing with drones. Normally, we need to do separate adaptations. Okay? It's not common to use the same algorithm. But in this adaptation, it's not so easy. So be careful with your time, because you have only two years, and you want to deal with other VRP variants. That I agree with that. It's the right way. It will. I think your thesis will be very strong if you do that. Okay.
Sure. Okay.
And I was A little question. You have some previous results on the second version of the new proposed algorithm that you didn't. You only present the algorithm, but you didn't have the algorithm, the island algorithm. Do you have some previous results on that you know the algorithm will be okay or not?
Actually, no, because you know, I was working on the code, but from I think from 2 months ago, something like this, I started working on the qualification text and the presentation, and started working on the other stuffs, and I didn't work on the code to have the results. No, I actually I don't have any results for that. If I had, I put at least some of them in the presentation. It was, I think it was useful, yeah. But I didn't have it.
As you mentioned, your intention is to compare some algorithm, not to the CFRP is just an application to compare this algorithm. And I believe you are on the right way. I think my comment is about that. Let me see if I have something else. No, I think that's all. Thank you again for the invitation. And I think you have a nice work, but a lot of things to do.
Sure. And thank you for your presence and accepting our invitation. Thank you.
Okay, Puka, thank you very much for your comment and feedback. I have a few words before we proceed. First, I would like to thank all the committee members for your participation. You were chosen because of your different backgrounds, and they complement each other to evaluate the work done by Babak. So this is why Razul has a very large experience on meta-heuristics and ICA itself and optimization. Gilberto Messa has a very strong background and experience on meta-heuristics, especially evolutionary algorithms, right? And Puka is the guy that has a strong background on VRP and local search meta-heuristics for VRP. So this is why we chose you for this evaluation, because we think they complement each other, and this is what we saw in this qualification. So I would like to thank you very much for your participation and all the comments about Babak's work. Okay. Regarding Babak, I have to must congratulate Babak for the work done so far. I have to say that Babak has faced some challenges since he arrived in Brazil for his PhD. He arrived in Brazil in a moment that we had a new government and new policies for the science and new budgets for the science, which were not very helpful to Babak during this course. But he managed to find a job, and he was doing this first 2 years of his PhD while working. So I think this is an information that adds to the quality of the work that he has done. And on the top of that, he also changed the topic. It was his initiative to change the topic during the PhD, so this was more challenging for him. But at the end, he managed to get some good results and present some nice ideas for the qualification, which is all his merit. So for this reason, I congratulate Babak for the work.
Thank you. Thank you.
You have some nice ideas, as everyone said, that you have the potential to produce a couple of journal papers which can qualify you for the PhD. So you have all the tools for doing this. And that's it. I'm very satisfied with your work. Very satisfied with your qualification as well. Regarding the multi-population, actually the island GA, this was kind of an imposition by me. I would like to explain this to the committee members. Actually, Babak brought this hybrid method combining ICA and AGS. And when I saw the ideas, many aspects of ICA, many ideas in ICA, they are quite similar to island GA or a multi-population GA. Now, both methods work with multiple populations, but there is an interesting aspect from ICA, which is the resource allocation of the method. Because in ICA, you have multiple populations, but those populations that are performing the best, they increase in size, and those populations that are not performing well, they decrease in size. So it's a kind of automatic resource allocation. We allocate more effort, more computational effort to those subpopulations that are performing better. This is something that I'm not sure if these ideas are used in island GAs, but they have some similarities. So this is why I told Babak, okay, you can just change the metaphor in which you based your method, and it worked the same as a multi-population genetic algorithm. So it was my suggestion to check these ideas, but this is something we need to, of course, advance and discuss better. Okay, Babak?
Sure. Of course.
But anyway, congratulations again for your work. Now we proceed to the third stage of this qualification, in which the committee members will gather privately to deliberate about the result. And for this, I would like to, Babak, to leave the meeting for a while, and then I will call you back to join us.
Okay.
And also, Luciano, se você puder interromper a transmissão. Ok. Luciano, a transmissão já está... Ah, ok. Muito obrigado. So Babak, it was a very fast deliberation by the committee members. All of them agreed that you are qualified, you have good work at hand, and you have all the tools to finish a good thesis. So congratulations.
Thank you. Thank you. Thank you all the committee members for your presence, your nice comments. I hope I can finish it with better results, that with higher level of the text, as Buca and Gilberto explained about the text, and I hope I can cover your concerns and in the meta-heuristic part also, dear Rasul. And thank you all. Thank you. And Federico, I forget about you. And thank you for your nice support during these 2 years. I hope I can have your support for the rest of the PhD also. Thank you.
It was my pleasure.
Bye-bye.
Good job.
Congratulations.
Congratulations.
Thank you.
Congratulations, Babak.
You have
Thank
2
you.
minutes
Thank you.
of a PhD. And would you like to take a picture with the committee members? Print
Sure.
screen?
Yes, sure. With the... Okay. Thank you.
Thank you so much.
Welcome.
Okay. Well, guys, thank you very much again, and that's it. Thanks, everyone.
Okay,
for
thank
watching.
you. Have a nice day.
Thank you.
Bye.
Take care.
Thank you. Thank you.
Bye.
Take
Have
care.
a nice
Bye.
day.
See you. Bye.
Bye.
Bye.